Hello everybody, my name is Ben and I'm here to go ahead and get this problem solved for y'all. So let's take a look at the problem. This is example 1.17 from the book, and as you see we have a two-component mixture in a liquid down here at the bottom of like a tube. And then these two components are going to evaporate and go kind of up the tube, and when they get to the top there's actually a stream of component 3 as a gas blowing across, and that's going to blow all the 1 and 2 away. So in this part of the tube, in this sort of gas vapor part of the tube, there's going to be components 1, 2, and 3. Now you can see down here component 1 is acetone, component 2 is methanol, and component 3 is air. And so it gives you some initial conditions for the mole fractions of components 1, 2, and 3 at the vapor interface. And it gives you this length of the, we'll call it the tube here. And that length goes from 0 to delta, and we're going to call that kind of dimension Z here. So there's diffusion going on here. There's flux created, right? Because 1 and 2 are flowing from the bottom of the cylinder to the top. And then, 3 though, I guess that's an important thing to note, is there flux for component 3? And the answer to that is no, right? Component 1 and 2 are flowing from the bottom to the top, but component 3 isn't flowing anywhere. So with that in mind, we can actually go ahead and say the molar flux of component 3 is going to be 0. And I guess I should talk about what's actually being asked for here. We're asked to calculate the molar flux of the 3 components, and we already knew the molar flux of component 1, or component 3, air, and we want the composition profiles, which would be a kind of a graph showing that as you go up the tube, what are the mole fractions of each of the components as you go up. So let's go ahead and let's go ahead and scale this problem. And you can see we start out with these Maxwell diffusion equations written up here, and I wrote up the equations for component 1 and for component 2. I already wrote those up just because they take a while to copy down and I didn't want to mess with it. So let's scale these equations a little bit and modify them somewhat so that they're easier for us to work with the computer. So first thing you probably want to, let's add in a scaling variable. And the goal behind a scaling variable is to set this up so that we are solving it from 0 to 1. So right now on the z-axis we're going from 0 to delta. Well, let's change this delta into 1. Well, how can we do this? Let's add in a new variable, and we'll call this new variable eta. That's an eta. And eta is going to be equivalent to, well, let's see. That's just going to be the distance you are up the tube. So like right here, whatever. That z distance up the tube. And then over delta, right? And that's going to go from 0 to 1. I'll write that down right there, 0 to 1. Now we're also going to add in a few other relationships to simplify this thing a little bit. First one is going to, actually I should probably solve this out a little bit more. So because we added in this this eta, we can actually work this eta into the Maxwell diffusion equation. And the way we do that is by setting up this. So you look up there, the change in concentration of 1 over d eta times d eta, that's really bad, the change in eta, which is our scaled variable, all over dz. See, that's the same as what we have right here, the Maxwell diffusion equation. Well, these two cancel, but we can also turn this term into something. And that term, look over here, eta equals delta over z. So if you move that z down, and then you take the derivative of it, you'll see that actually that's equivalent to the change in y1 over the change in eta times 1 over, and I always forget how to make deltas. They're kind of hard to make, I'm not a huge fan of delta, drawing it at least. That brings in a 1 over delta. Now, if we were to plug this in right here and kind of solve it all out, we would actually bring in a delta to our Maxwell diffusion equation. So let's simplify the things we know. We know the concentration because we know that concentration equals P divided by RT, R being the gas constant, P and T being the pressure and temperature, which we're all given those things, or we can find them from literature. And then we actually already know these diffusion coefficients. They're given to us in the problem. So yeah, with that in mind, we can go ahead and say that, with that in mind, we can go ahead and add in this new variable f, and the f is going to correlate to a d value, or a diffusion coefficient value, and it's going to be the concentration over delta. And this stands for 2 to 3 and for 1 to 3, but it's going to be just different, just with a different diffusion coefficient value. So I'll flush that out more as we're programming this, but yeah, suffice it to say that's what we need to do. Now we also, in order to solve for the mole fluxes, we need to make an order of magnitude estimate for the mole fluxes. So how can we go about doing that? Well, let's just take one term of the Stefan-Maxwell diffusion equation and try to solve it out with order of magnitude estimates, and see if we can't kind of, figure out where are we trying to go with this and get a good starting point for our root function. We have a root solver, and we're going to use that to solve things. So, let's see. The change in concentration of 1 over the change in eta. And my etas are so bad, I feel. It's a great point of shame for me, really. And we got this same thing as before. And then we have this f on the bottom. And this is just the f we brought in before. So this f is going to equal, and I'll just write out the order of magnitude. So we have the delta. The delta is an order of magnitude of about 1. I'll just make these like equivalent. They're about the same, And then we have the d. So this diffusion coefficient is going to be the order of magnitude of 10 to the negative 5th. That's just something you have to know because it's gas, and that's the diffusion coefficient. That's just something you have to kind of know the order of magnitude of. And then we have P over RT. C equals P over RT. Well, T is going to be about 300. P is going to be about 10 to the 5th pascals. R is going to be about 8. So we got a 10 to the 5th on top. We'll call that 300 times 8. We'll say it's about 10 to the 3rd. That's a pretty rough approximation. But these two are going to cancel. The 1 is going to be there. So we're just left with a 10 to the 3rd on the bottom. Now over here, let's take a look. The change in y1, well, that's going to be about 1. About. The change in eta, we defined eta as from 0 to 1. So that's going to be about 1. Okay. So these two concentrations right here, these are just going to be about 1, right? So about 1, about 1. And that leaves us overall with the difference between the two mole fluxes over 10 to the 3rd is about equal to 1. Well, with all that taken into account, we can just find that our estimates for N2 and N1 must be about 10 to the negative 3rd. That's the only way it's going to cancel this out. So, yeah. Now we're going to boot up a computer and use these initial guesses we got to kind of solve the function. So, yeah, just stick with me for a second, and I'll get that loaded up, and see you there in a few. Hey, everybody. So now that we've got this loaded up, let's go ahead and talk about this and try to work something out here. And yeah, let's go ahead and just start trying to solve out this formula. So yeah, so we have the problem given to us right here. Except no, we actually don't have the problem. This isn't 1.17, it's 1.16. Here's 1.17. Silly me. I'm such a silly goose. Am I recording? Yes, I am recording. Yeah, I don't know. That just gave me a lot of fear, So now we have to start out by importing some things, and this is telling Python to go to these specific locations on the internet and pull functions from here. So import numpy. That is that's sort of a number calculator we're going to use for complex calculations. Yeah, and then SciPy. SciPy is something we're using to we're using some scientific functions to kind of solve and optimize. We're solving an IVP, an initial value problem. And we're also trying to solve a root function. So yeah, a root is solve when it's equal to 0. And then these plotlies we are bringing in order to kind of solve the, what's the word for it? We're trying to use these to build a plot of the data. Yeah, so now let's go on ahead and we'll run this cell real quick. And yeah, now we're ready to go on the second cell. So next up, we have to, let's put in some of our given data. So we know the pressure we were given was 0.5 pascals. That's not true. That's the temperature, and it's in Kelvin. That's so silly of me. The temperature we were given was, and the pressure we were given was, well, let's take a look. That's OBS. Here it is. So the pressure we were given was 99.4 kPa. Now we're going to bring that in as pascals, so we're going to multiply it by 10 to the third. And then we need R. So R is going to be 8.314, and that's the gas constant. And then, yeah, after that, we can solve for the concentration, actually. So the concentration, I keep messing it up. It's kind of the nervousness. I've programmed this out many times before. I just can't type all of a sudden, you know? Yeah, the concentration, that is going to be, that's going to be P divided by R times T. And once again, that's from the ideal gas law. And then we have delta, which was just given to us. That's the distance from the bottom of the tube to the top of the tube. And I'm looking at the board right now, by the way. So that's what I'm looking at right now. And that's going to be actually in meters, which makes sense. And now we'll go down and we got these diffusion coefficients. And that's going to be 8.48. Now it's given to us in millimeters per second, or millimeters squared per second, but that's not really what we want. We want in meters squared per second. So let's multiply it by 10 to the -6th. Now, these define Maxwell diffusion coefficient from 1 to 3 is going to be 13.72. Once again, we're going to put that in meters per second, meters squared per second. My bad. Don't want there to be any confusion. And then we got 19.91 for the last one. That's times 10 to the -6. Once again, converting meters to meters. Now let's add in these F values. So I talked about F earlier. That's going to be C, the concentration, which we solve for right here. That's the total molar concentration, times the corresponding D value, the corresponding diffusion coefficient value, divided by delta. So yeah, let's just go ahead and copy this down and change the numbers around a little bit. And then we will copy it one more time. And now we'll do it from 2 to 3. Yeah, and these are just going to be used so we're not having to type out C, D, and delta all the time. You know, that's just going to simplify this a lot. Now we should go ahead and put in our initial guesses. So our initial guesses for this are going to be, actually, we'll put in our initial values. So what are our initial given values, right? They're right here. In one of their experiments, the composition of the vapor at the liquid interface was Y1. So the composition of, or the concentration of component 1 is going to be 0.319, and then of 2 is 528. So, yeah. Yeah. And then these are the initial values. Now we also have some initial guesses, and those were the estimates we made earlier. So those are abbreviated with an I as well, but those are not, yeah, those are, these are initial guesses. So I'm gonna show that in a second. But yeah, these are the initial guesses for the molar fluxes. So these are in the right order of magnitude, but they're not the actual number. They're not actually true anywhere. And then I'm putting guesses there in caps, so that way everybody knows what's going on, you know? Yeah. So now we're ready to try and solve the IVP. We've imported all of our variables and everything. So here's the solve IVP function, and this is something we called earlier. Now, the solve IVP function has a function, so we have to give it a function. In this case, we're giving it two functions in the form of an array. Time span, so that's 0 to 1 here, an initial condition, a method, and then some other things that we kind of don't need to worry about too much, except for one of them. But first we need a function, so let's go ahead and write out a function. So we're going to define this function. We're going to call it dy max-Stefan, so it's the Maxwell-Stefan equation relative to dy. We're going to put the independent variable first, the eta, and then the dependent variable, in this case it's y, but y needs to be an array, right? Because we have 3 values for y. We're going to condense it down to 2 values, but yeah, we have 3 values for y normally. So y1 is going to be, or the molar concentration of 1 is actually going to be the first value in the array. So that's going to be y sub 0. So that's pretty important. In Python, you start from 0. So the first component in an array is the component number 0. That's a pretty important thing to keep in mind. And how well am I showing up in the camera right now? I'm showing up super well. I'm glad about that. Yeah. So then, and y3, once again, in this whole thing, we're going to solve, to keep this matrix more simple, we're only going to solve y3 in terms of 1 minus y2 minus y1, like this. That's how we're going to solve for the concentration of air all throughout this. So yeah, now after we've defined all the variables in a function, we need to return something. So we say return, and now we need to return an array. So yeah, np.array, and we put something in this array, and we can just list whatever we want to put in the array. So actually what we want to return this array is the Stefan-Maxwell diffusion equation. So what is that? Well, it's going to be this. And I talked about this before when I was up on the board. This is kind of just from literature, so I'm going to go through it pretty quickly because it takes a while to type out and say all that. But yeah, so yeah, so that's the first Stefan-Maxwell diffusion coefficient. Now notice we don't have an equal sign in there. It knows that this equals, it knows that this one equals the solution to this one is equivalent to eta. It knows because of the way we've set up the problem, because we put the independent variable into the dependent variable. Then up next we have, for the Stefan-Maxwell diffusion coefficient for component 2, and that's going to be, that is going to be this, yeah. And once again, we've kind of discussed these before, so I'm kind of assuming you know how these are derived. Keep in mind, why is the second function, second term shorter than the first term? That's because the second term has the molar flux of component 3 in it. And the molar flux of component 3 is going to be 0. So that whole term is going to be 0. So that lets us cancel some things out and not have to worry about the molar flux for component 3. So let's go ahead and fill in the solve IVP. Well, our function for the solve IVP is going to be dy max-Stefan, right? And the function we just set up. The time span, that's from 0 to 1. That's the whole point of adding eta, was so that we can define it. Now this y0, that's the initial condition. So we know those. That's just y1i and y2i. The initial conditions for the molar concentrations. And then the method. Now, I don't really know too much about the specifics of method. This is how it's actually going to solve out. This is like the math is going to use. My professor loves Radau, and I'll do whatever it takes to get a couple brownie points. So, yeah. And then at the end here, all we need to worry about is this dense output. And this is just there so that we can call this as a function later and solve it. So I'm going to go ahead and run this, and we're going to get an error. And then this error is going to show what we need to do next. So look at this. Yes, that's the error I wanted to get. But the first time I've ever heard someone say that. Look at this. Name n2 is not defined. Well, what does that mean? Okay, that means that, wait, we have this n2 here. We also have an n1, but those aren't defined. We didn't define them up here because we don't know them. I spelled initial wrong there. I'm going to leave it, I'm going to let it stay. So let's go ahead and set up another function. We're going to call this function mole flux guess, just to describe, and we're going to use this function to kind of guess the molar fluxes. So we have this one set up as an array. So we're going to do something similar to what we did before, right? With the n1 and n2, and then we're going to move this function actually inside the other functions. That way we're building one kind of big function. And then let's set this kind of solve IVP, let's set this equal to res as kind of a temporary variable. Res is just a temporary variable we're going to use inside of here. And yeah, after we solve res, we are going to return. So remember, we're returning from this function right here. We're returning from mole flux guess. We're going to return, what do we want to return? Let's return res solved at 1. Now, why would we solve res at 1? Well, this is the initial value problem solved. This is the initial value up here solved. And the goal is, for the next step, we're going to use this root function. And this root function will solve for, I said rot. This root function will solve for when the functions, when its independent variables, or when its dependent variables are equal to 0. So think about it. This is solving it when eta is equal to 1. Well, when eta equals 1, and I'm looking at the chart, and I'll put it up on the screen, when eta equals 1, the concentrations of components 1 and 2 are actually going to be 0. So this works out perfectly for the root solver, right? Those are going to be the zeros. So now that we know this, we'll say, let's see, what do we need here? We need a function. Well, the function is just going to be mole flux guess. Then what's next? Oh, we need initial guesses, right? X0 means initial guesses. Well, let's scroll on back up here and take a look. What are our initial guesses? There they are. It's N1i and N2i. We solve those out using like the scaling. Yeah, so we'll just put those in. And yeah, I think that should be good. We go ahead and solve this out and look at that. Ooh, something went kind of wrong here. So if you give me just a quick second, I'm going to take a look through everything I've done. And, ooh, okay, so this is supposed to be 0.528. I put in one of my initial values wrong. Let me run that cell again. Run that cell again. Let's try running this cell again. This is what I expected to see. And I've just ran this so many times. I know that it's supposed to go through 30 iterations, and I know what the final array is supposed to look like. So that's why I'm able to solve this. So let's set this root function equal to some variable. We'll call it this variable mole flux. And yeah, so now we can run this, and now mole flux is just a variable we can call. And then mole flux, we can hit actually .x, and .x is basically telling it, hey, we want to see the matrix, or we want to see the array returned by this root function. And now we can even call one of the values in the array. So we could just call the second value by calling 1. And now look at that, we have that second value. So now we actually know the mole fluxes for components 1 and 2. It's the two components in this array. So let's go ahead and just define these as N1, or the molar flux of 1 is going to be, mole flux of 0. And then, yeah, same thing below with mole flux of 1. Yeah, so look at that. So that's pretty helpful, but this, if you recall back to what we were doing a couple minutes ago, we can go back and we can take this equation, right? This Stefan-Maxwell equation we put together earlier, and now that we know the mole fluxes, we should be able to solve the initial value problem and get an actual value, right? So let's go ahead and do that. Let's just copy this, and I think I didn't copy it, so that's kind of unfortunate. We'll copy that down. Boom, there it is. And yeah, let's see, is this function all set up? Yeah, I think it's ready to go now. But so what are we solving out here at the end? The solve initial value problem is solving this Stefan-Maxwell equation from 0 to 1 for when eta equals 0 to 1, based on the initial value conditions using the Radal method, and it has this dense output is equal to true. So what is this actually giving us? Well, this is actually going to give us the mole fractions, so which I'm going to abbreviate as mole frac. So if we go ahead and run this, and after that, let's do maybe molfrac dot solve, which is telling solve the mole fractions at component at 1. Well, what do we get? What should we get at component 1, I guess? Don't look at what I solved yet. What should we get for component for at 1 when eta is equal to 1 for the mole fractions? We should get 0 for 1 and 2, right? So let's see, what do we get? Oh, it's a negative number. Oh, wait, no. It's actually okay, because even though it's a negative number, it's times 10 to the negative 13, which is basically 0 as far as I'm concerned. Also, those aren't the values I've usually gotten in the past. So something's probably wrong here, but I'm not quite certain what it is. So I'm going to go on ahead and try to keep working this out. And, oh, yeah, it's something up in here, I believe. Let's see. I don't know. I guess I'm just going to have to keep going about solving this formula and see if we don't come up with something. So yeah. So now what do we have? We have this molfrac, and this molfrac returns to us an array, and that array is the values of components 1 and 2 at any eta value. So with that, we can actually go through, and we're ready to plot this. All we need are a bunch of x values. We plug it into our formula. We get a bunch of y values, and then we're good to go. We can plot those out. So let's generate a bunch of x values. I'm going to call this one plot eta. And what should plot eta equal? We're going to use something called Linspace. Linspace is from the NumPy library we imported earlier. And Linspace is something that's commonly used in programming, and it's basically just going to give me an array of equally spaced values from whatever I start from, which will be 0, to whatever I end at, that would be 1. Remember, this is eta. Eta goes from 0 to 1. And the number, we'll say 51, so it generates nice and prettily. So plot eta, I just want to show it to you all. It generates this. Look, that's so pretty, isn't it? I love it. I'm so happy about it. And yeah, so now we need some y values. So we'll call this plot molfrac. Yes, that would be a good thing to call it. And plot molfrac is just going to be molfrac solved at those plot eta values. So let's see, and these values might be messed up. This may be when I go back and try to figure out what error I've made. I've probably defined something wrong, and oh no, look at that. This all looks pretty good. See, look at this array. So there's two arrays here, right? One goes like the top, one is this bottom array, and yeah. So look at this. It starts at the starting value we gave it, 3.19, which is that the right starting value? Yeah, 3.19 and 0.528. 0.319 rather, and then it goes down to 0. So that's what we would expect, right? We would expect the concentration of acetone, component 1, to start out at the starting value and go down to 0 by the end of that tube, when we get to the end of the tube. So that's all good. I'm actually going to get rid of that because that's just kind of, it's too much information. It kind of blurs up the screen. And yeah, now we're ready to plot it. So whenever you plot something, you have to start out with a figure. You have to basically set it equal to something. So we're going to take this make subplots thing I imported earlier. So fig, that's our figure, equals make subplots. And then we need to tell subplots how many rows we need. Well, we only need 1 row and 1 column. And that's all we really need here. It's not too complicated of a graph, although you can do some pretty cool things. And now we have to add stuff onto this graph we've created. So let's do fig.add, I typed something inappropriate there, accidentally, add trace. Now add trace is just another word for graph in kind of the lingo of this library. So yeah, we're adding a trace, and this trace is going to be of the variety subplot. So we're going to, yeah, does this bring up something? Well, let me see if I can get the helper to come up. I can't get the, oh, let's see. The helper should be coming up, but it's not. So that's making me a little bit concerned I've done something incorrectly, but who knows? I think it's okay. So now in this go scatter, okay, the helper came up correctly. So this scatter, this is basically saying we're adding a trace. The type of trace is a scatter plot. And the x values of the scatter plot are going to be from what array? Well, they're going to be from plot eta, right? So from plot eta, now we need the y values. So where are the y values? What array are the y values going to come from? Well, that's going to be plot molfrac. But hold on here. Do we just want plot molefrac? Not exactly. We want the values from the first array in plot molefrac. Remember how plot molefrac gave us, or the plot of the mole fractions gave us 2 arrays of 51 values each? Well, this is what we actually want. We want, we want for this first component. So, and then we got to name it. I'm just going to name it acetone. Make sure you have the name as a string. And yeah, let's go ahead and plot this and see what it gives us. And look at that. That's perfect. That's exactly what we want to see. So it starts out at the initial condition given, right? And slowly, or kind of gradually, it fades down to 0. That's what we would expect acetone to look like as we're looking through this tube. So yeah, I'm going to copy this all down because, as my professor would say, I'm not a lover of pain. And I'll just change the little value right there and change this one so it's methanol, right? Because this is component 2, so it's methanol. So now we look at that, and look at that. We have a nice little thing off to the side labeling it. Look at that. Starts out at the initial condition, goes down to 0. Now air. Air's a little bit different, but the same concept. How do we calculate air? How do we say we were going to calculate air throughout this whole example? This is kind of my favorite part. I think it's so simple and it makes things so easy. Well, we're actually going to calculate air by doing 1 minus the other 2 components, right? Because it's a 3-component system. So we just set that up right here. 1 minus the value from molefrac 1 minus the value from the other component molefrac. And that's actually going to give us the concentration of air. So let's change that to air. Okay. And air would do how we expect. It starts out pretty low at the initial condition given, right? We didn't really use this at all because it's just 1 minus the other 2, but this is the initial condition for air. It was given to us. And yeah, it's going to go up until at the end of the system, at the end of eta, air is 100% of the moles. So there's one more thing we can do here. Because right now you look at this chart, and this chart is, it's good, but it's in terms of eta. Eta is a variable we made up for scaling purposes. So I don't really think we should leave this chart in terms of eta. We should try to change this chart around so that it's actually in terms of, well, what should we make it in terms of? We should probably make it in terms of delta. And I was looking over here. I have my phone over here as a timer, just so I know how long I've been running for. Yeah, so if you were wondering why I looked over to the side, I didn't want to come off as I was cheating, you know. So yeah, let's see, how do we change this? Well, we need to change the x-axis, so we're going to change plot eta. And remember, what's the definition of eta? I'm looking over there at the screen, and I will show you a picture of this. Eta is equivalent to z over delta, right? Well, in order to turn eta into z, just multiply by delta. It's pretty simple algebra. So we know delta. It's pretty easy. So let's just put that in there. Put that in there. Multiply it all over and go ahead and look at that. Now it's in terms of delta. So this is the bottom of the tube. This is at the liquid vapor interface. Over here, we're all the way at the top of the tube. And you can see there's no methanol, no acetone, and there is all air. So let's go look in the book, and what does the book say? Well, the book says that the molar concentration should be, and I got to keep going for a little bit because it doesn't seem to want to just tell me. How rude. Yeah, here's how the book did it. The book did it in a weird, convoluted way that no one likes. And if no one likes it, no one should do it. Well, these are the mole fractions we got. These are the correct mole fractions, right? We were given these in an array. You could go back and take a look at that array. In fact, maybe I even left the array displayed. Oh no, I didn't want to show OBS. It ruins the magic for you all, you know. So we could just display, well, boom, there's our 2 values for molar flux, right? Right, boom. And they're slightly different, but I mean, they're basically the same. And then these are the experimental results, which are about the same. And then, let's see, does it give us a chart? Yeah, look at that. So there's a chart. That's the chart that was given in the book. And, well, here's the chart we generated. It looks a little bit better maybe if I put them up against each other. Yeah, look at that. So, yeah, the charts look about the same. And those points on there are experimental data. So, yeah, thank you all for watching. And I hope you learned a lot. And if you didn't learn a lot, I hope you at least learned something. And, yeah, have a nice day. Bye-bye.